Hello everyone, welcome to Unacademy. My name is Mohana, and today's class what we are going to do study is sorry, just a second guys. Okay, sorry guys, just a second. And right, okay, I am online, and today's class we are going to learn about what is a dimension, okay, and what do we mean by dimensional analysis, and followed by what are the applications of dimensional analysis. All right, so with that note, let's begin. Once again, my name is Mohana. I'm a physics educator here at Unacademy, and this is my Telegram channel. You can follow me in the Telegram channel, and also this is the common ICSE and ISE board channel. You can follow this channel as well. So you can give the answers basically in the chat box. So what do you think? Which of the following is not a fundamental quantity? So here we have mass, basically length, okay, time, velocity, and temperature. So over here, if you see, mass, length, time, all of these and temperature are basically fundamental quantities, but velocity is a derived quantity. So this is not a fundamental quantity. All right, Akshay, that is right. Velocity is not a fundamental quantity, right? So basically, according to SI system of units, we have 7 basic quantities. That is basically we have if you know what are the fundamental quantities, you can actually give it in the chat box. So if you know, we have mass, right, and then we have length, then we have time, right? All of these are fundamental quantities. Actually, temperature is another fundamental quantity. And then if you have luminous intensity, amount of substance, all of those are again fundamental quantities, right? Electric current is a fundamental quantity, right? Luminous intensity is another fundamental quantity, right? And then if you see, obviously current is a fundamental quantity, and amount of substance, right? Amount of substance is also a fundamental quantity, right? See, we have 7 fundamental quantities, and all using these 7 fundamental quantities, you can get the derived quantities. For example, if you actually see what is velocity, for example, okay, velocity is nothing but distance by time. So the unit of distance is basically your measurement is actually in length, right, by time. So if you see, velocity is a combination of 2 fundamental quantities, right? So you can get your derived quantities from fundamental quantities. So for all of these fundamental quantities, okay, if you can actually give an associated dimension. All right. So actually, velocity being displacement upon time is right, because displacement, velocity is a vector quantity, so we give it as displacement by time. If you take distance by time, again it becomes speed, which is a scalar quantity. Alright, now if you see dimensions of each of these fundamental quantities, so whenever we give dimension of a particular quantity, we give it within the square bracket. So dimension of length over here is capital L, and we give it upon this quantity, right, the square bracket. Dimension of mass, again if you see, is basically we give again capital M, we give it without the square, within the square bracket. Time is capital T. Again, for electric current it is A, right, capital A. Dimension of electric current, we give it as capital A. And temperature, again Kelvin, so give it as capital K over here. And in case luminous intensity, candela, we give the dimension as CD, and amount of substance is mole, right? So these are the dimension for the 7 fundamental quantities. So given that, what is dimension of a physical quantity? If you can represent, okay, dimension of a physical quantities are the power or exponent to which the fundamental quantity must be raised to, okay, to represent the quantity completely. Okay, so for example over here, if you take velocity, right, velocity is actually, if you see, not distance, you can give it as displacement upon time, right? So velocity is actually displacement upon time. So the unit of displacement, if you see, is basically L, right? So the dimension of displacement is measured in terms of length, right, which is basically gives you L. Okay, dimension of length is L, by time is T, right? So L, and when this T comes to the numerator, it becomes T to the power minus 1. So here you can write mass quantity, right? Velocity does not have mass, right? So mass is basically m to the power of 0 just means 1, right? Mass quantity becomes 1, okay, into the dimension of length if you take is basically 1 over here. So velocity over here has nothing but it has a dimension of velocity. Okay, the dimension of velocity, the dimension of mass is 0, right? Dimension of length if you take is basically 1, and dimension of time if you take it is basically -3. Okay, so this is dimension of velocity, right? So dimension of a physical quantity is nothing but the powers to which the fundamental quantities must be raised, okay, to represent that quantity completely. Now that we saw what is for velocity, let's see one more example. Okay, for example, a very simple quantity we'll take. What about if you want to find for very simple one. What if you want to find for density, right? Density is given by mass by volume, right? So again, whenever you want to find dimension of any given quantity, first you have to write each of that quantity in terms of the fundamental quantities, represent each of the derived quantities in terms of fundamental quantities. Mass is a fundamental quantity, but what about velocity, volume? Volume again is not a fundamental quantity, right? So volume can be given as, for example, volume you can give it as length into breadth into height, right? Now all of these becomes a fundamental quantity. Now if you see, density is given by rho. Now if you see what is the density of fundamental quantity of density. Now fundamental quantity of density is nothing but on numerator if you see what we have mass. So dimension of mass is m. Now dimension of length over here is again L, right? Again dimension of breadth, the measurement, again breadth we measure in terms of meters or centimeters, right? So it has the dimension of length. Height again has the dimension of length L again. So what we have over here, okay, dimension over here becomes m, right? And L to the power of 3, when it comes on top, it becomes L to the power of -3. So dimension of density, if you see, what do we have? We have mass has the dimension of 1, right? And if you see length, the dimension is basically -3, and if you see time, the dimension is basically 0. T to the power of 0 is just 1, we know this, right? So this is the dimension of density. Yes, Akshay, you got the dimension of density right, right? So let's carry on. Let's see what is basically what is the dimensional formula of force? What do you guys think is the dimensional formula of force? You can give the answer in the chat box. So again, force, first you have to represent it in terms of fundamental quantities. I mean, you can, this is a derived quantity. So force is nothing but mass times acceleration, right? Akshay, that is right, right? Mass, again the unit of mass, again mass, if you see the fundamental quantity of mass, the dimensional quantity if you see is m. What about acceleration over here? Acceleration is basically L t to the power -2, right? So this is the dimension of force. So option C is the right answer over here. Acceleration, again if you see, acceleration is rate of change of velocity by time. Velocity is L t to the power, right? L t to the power -1 by, right? Acceleration, if you're taking dimension of acceleration, is dimension of velocity. Velocity is L t to the power -5 by time t, right? So when this comes on top, this t, when it comes on top, it will become t to the power of -1, and again here there is already a -1, so it becomes t to the power of -2, and dimension of mass is m. So you get dimension of force as m L to the power -2. Right, so this is how we generally find a dimensional formula. So whenever you have a quantity, write them in terms of the fundamental quantity, and from there you can substitute for each of the fundamental quantity the associated dimensions. Okay, now what is dimensional formula? Very simple. Right now we said what is force given by m L to the power t to the power m L t to the power -2. So for force, this is the dimensional formula. So the expression which shows how and which of the fundamental quantities represents the dimension of a given physical quantity. This is basically dimensional formula. Now there is another term which is called as dimensional equation over here. Dimensional equation is very simple over here. Okay, if you can represent the dimensional formula, in this case we know for force the dimensional formula is basically mL to the power -2. Now the equation obtained by equating the physical quantity, okay, with its dimension. Here this physical quantity is force. Force has a dimension of mL to the power -2. So this equation that we are seeing over here, this equation we actually call it as a dimensional equation. So this is the difference between your dimensional formula and dimensional equation. Alright, now knowing this, let's carry on. What are the applications of dimensional analysis? So before that, what is dimensional analysis? Okay, so if you start the method of studying any physical phenomenon on the basis of dimension, then we call it as dimensional analysis, and it has three major applications. Okay, first application is to convert a given physical quantity from one system of a unit to another. Okay, now second quantity is very simple, to check whether the correctness of a given physical quantity using dimensions. Okay, the third application is to derive a relationship between different dimensional quantities. Okay, so we are going to check each of this. Okay, we will try and solve each of these cases. Okay, so the first application, what we saw, it was to convert the physical quantity from one system of unit to another. Right, so the first application, if you see, it is just based on the principle that the magnitude of a physical quantity remains same whatever the system of unit may be. For example, okay, if you take 1 centimeter, okay, 1 centimeter, if you take 100 centimeters, 100 centimeters is nothing but 1 meter. Right, so we write 1000 grams is nothing but 1 kilograms over here. Right, centimeters and grams, these are actually what? These are units of, these are actually the fundamental, these are units in case of CGS system. Right, so in this case, if you see meters or kilograms, these are units in case of SI system of units. Right, but we know dimensionally, if you look at the magnitude alone, if you look at 100 centimeters, if you look at this 100 centimeters and 1 over here, okay, magnitude in both cases are same. Why? 110 centimeters in this case obviously means 1 meter. So 1000 grams again obviously means 1 kilogram, right? So in this case, what we are seeing is very simple, to convert the quantity from one system of unit to another. Okay, this is just based on the idea that the magnitude of physical quantity remain the same whatever the system of unit might be. Okay, so let's say Q over here represent a fundamental quantity. Okay, for example, the fundamental quantity could be mass. Okay, and N1 U1 would represent what is the magnitude and unit in one system of unit, which is actually equal to N2 U2, which is basically gives us the idea of the magnitude as well as the unit in another system of unit. For example, okay, let's see this with an example. Okay, here we just said that if you take something like mass, okay, mass of an object, okay, so this is basically nothing but Q, which is equal to, let's say in SI system of unit we are taking 1 kg. Okay, so mass in SI system of unit that we have taken, we are taking it as 1 kg over here. Right, so in one system of unit, what we are saying, this mass is equal to 1 kg. So the numerical 1 over here will be basically N1, kg we are taking it as the unit U1. Okay, now similarly this is equal to what? 1 kg is equal to what? 1000 grams. Right, so this 1000 over here would be N2. Okay, this is in terms of SI system of unit, this is in terms of CGS system of unit. Grams over here is actually equal to U2. Okay, so here if you look at the units U1 over here, this U1 that we have over here can be represented in terms of dimensional quantities, right? So we can write this particular quantity U1 as, okay, mass, okay, because it is for the first system of unit we have taken. Let's write this as M1, okay, then let this be L1 T1, okay. We are writing in terms of their mass, length and time, okay. And in this case, if you're taking, okay, in this case any system of unit, now that we know what each question represents, okay, let's remove this and let's say the power term it might have, okay, any physical quantity. If you're generalizing it for any physical quantity, then m to the power it could be a, right, any quantity. The a could take whatever the physical quantity you're taken as. In case if you're taking this for mass, then a would basically be 1, okay, and b in this case that we are taking, this will be equal to 0 and t over here will be again equal to 0, right. Similarly, this is U1, means let's take U2. U2, again this unit can again be the unit of the second system that we have taken, that again can be represented as, right, M2, okay, L2, T2, right? So again all of this to the power a, b, c, right? So substitute this in this particular given equation. What we know, n1 u1 is equal to n2 u2, right? So m1 a, l1 b, t1 c, right? This value into n1 into this value is equal to n2 into this value over here, that is m2a, okay, l2b, t2c over here. Okay, now that we have given this in this terms, right? So just a second guys, I'm really sorry. Okay, now what will be n2? If I want to find n2 will be what? Very simple, n1 into, right? Then we have this individual quantities, that is m1a, okay, l1b, t1c divided by this quantity over here, okay, divided by, we have, okay, let's divide each of the individual quantity over here, right? Divided by m2, right? Both of them has the power term a, divided by l2, both of them has the power term b, then l2 over here, both of them have the power term c over here, right? So these power terms can be taken commonly, right? And from here we get an equation, right? If you know one quantity, okay, if you know one quantity over here, for example, if I say we are measuring some length, and I am saying in one system of unit it is 1 kilometer. Okay, now for example, okay, let's go with mass again. Let's go with the same equation we have example we have taken. Let's take mass. Okay, let's say in one CGS system it is equal to 1 kg. We know it is equal to 1000 grams, but we want to find what is N2. Okay, what is this value over here? 1 kg is equal to how many grams? Then we can make use of this equations. We can make use of dimension to find the to convert from, to find how much is 1 kg in terms of grams. Okay, so let's see that. Let's do one example in this case using this equation. Okay, so let's convert an easy one. We will do. Let's convert. Let's basically convert 1 joule. Okay, 1 joule is the unit of energy in a CGS system. Okay, so we have 1 joule and we want to know this 1 joule is equal to, this is in terms of SI unit, we want to find converted to CGS system of unit, and 1 joule, okay, yes Akshay, that is actually right. Okay, 1 joule is equal to how many urges. Okay, so again unit of energy in a CGS system if you take is urges, right? So all we want to do is whatever is in SI unit, we want to convert it into CGS unit, and we want to find how many is that. Okay, now if you see, very simple over here. So here what we have over here N1. Okay, we know what is U1 over here. Okay, we don't know, we want to find N2, and we know what is U2. This is what we want to find. All we have to do is we want to find what is N2 over here, for which we can make use of this equation over here. Okay, so coming back to this equation over here, how would we find this? Very simple. Okay, all we have is, we have the direct equation. We know N2 is equal to N1 into, okay, mass of the unit in the first unit, M1 by M2, right, the whole to the power of A, right? Then we know L1 by L2, the whole to the power of me. Then we have T1 by T2, the whole to the power of C. Now let's take SI unit of energy, right? If you take for energy, right, joules, the dimensional formula for energy, if you're saying what is the dimensional formula for energy here, the dimensional formula for energy is nothing but M, okay, L to the power 2, T to the power minus 2. Okay, that is the dimensional formula of energy. I am directly giving the dimensional formula over here. Alright, so this is basically the dimensional formula of energy. Now from here we can actually look at the power terms, right? So basically if you compare the power terms, what we get certain quantities over here. That is, we can see that A over here, this value of A over here is actually equal to what? A is actually equal to, in this case we have 1, and B is actually equal to what in this case? B is actually equal to 2, and C over here is actually equal to minus 2. Okay, these are the values of A, B and C. Okay, now we have to substitute for the known quantities with the unknown quantities. Okay, so here if you see, with respect to, okay, let's try substituting in this equation that we know. Okay, let's try substituting directly in this. Okay, so here what do we know? Let's try substituting in this. We know in SI system of unit, right? In SI system of unit, the mass is actually given in terms of 1 kgs, right? Another one what we want is in terms of CJ system of unit, right? So since CJ system of unit, if you see, the grams are given, unit is actually given in this case in terms of grams, right? Now power term A, what we have over here, equating them to the dimensional formula, A we found as 1, right? Similarly, we will substitute for the other two cases as also. Okay, so similarly for the other two cases also we will substitute. Now over here, what will be length in case of the second quantity? Length over here is going to be in case of CJ system, it is going to be 1 meter. In this is in SI system of unit it's 1 meter. In CJ system of unit it's going to be 1 centimeter, right? So L to the power of what we have over here, 2. Okay, now similarly if you see another quantity that we have in this case is basically time. Time in both systems, if SI system is also 1 second, CJ system is also 1 second. Okay, so both to the power -2. Alright, now very simple, we want to cancel the units over here, which means, right, we want to convert everything in CJ system to SI system of unit. So whatever is in CJ system over here, write them in terms of SI system of units, right? For example, in this case if you see, 1 kilogram is nothing but 1000 grams, right? And similarly 1 meter is nothing but 100 centimeters. Okay, very simple, that's it. Now what we can do, okay, now what we can do is basically we can actually, okay, let me just get this out of my way. So over here now what we can do, we can actually cancel the terms. Okay, all the power terms gets cancelled, and N1 if you see, we just want to find what is the value of 1 joule. So right, so N1 over here is going to be 1. So N2 is going to be 1 into this is going to be 10 to the power of 3, right? This is going to be into 10 square. This is going to be 10 square the whole square, right? 10 square the whole square into 1 to the power of -2 is just going to be 1. So N2 over here is going to be 10 to the power of 3, right, into 10 to the power of 4. So N2 is going to be 10 to the power of 7. So what we get over here, 1 joule if you take is actually nothing but equal to 10 to the power of 7 ergs. Alright, so this is, we can convert from one system of unit to another using dimensional analysis. We can find what is the magnitude, okay, of a physical, we can convert one quantity from one system of unit to another. In this case we found, using dimensional analysis, we found in this case we found that 1 joule is equal to 10 to the power of 7 ergs with respect to CJ system of unit. Okay, this is one application. Now going past to what is the second application that we have for dimensional analysis is that it can be used any given equation, any given physical quantity. Okay, we can check where the correctness of a given physical quantity. Okay, so in this case, to find the correctness of a given physical quantity, okay, we are going to make use of principle of homogeneity of dimension. That is, physical equation will be dimensionally correct if the dimension of all terms on both sides of the equation are same. So a given equation, we can check whether that equation is correct or not using dimensions. Okay, so let's do a very simple question over here. Okay, let's check the dimensional correctness of this equation. S is equal to ut plus half at square over here. Alright, so if you see, right Akshay, you have to see that both sides of the equation that we have, whether it is dimensionally correct or not. Okay, so let's do this over here. So we have, okay, from the equation of motion, right, second equation of motion, S is equal to ut plus half at square. Now if we see that this equation is dimensionally correct, if you want to say, whatever is on this right hand side over here, what we have, the dimension of S over here. If you see, the dimension of S displacement we are talking about is basically dimension is L, right? So right hand side we have the dimension L, okay? Left hand side also we should make sure that the dimension we are getting should just be L. Okay, for example, what is the dimension of u into t? Okay, u into t if you see, okay, u into t if you see, u is nothing but, okay, u is nothing but in this case velocity, right? Dimension of velocity is what? L, t to the power minus 2 into what is the dimension of time over here? Sorry, L t to the power minus 1, right? It's velocity. So L t to the power minus 1, okay, into what is the dimension of time over here? T. So what do we get for this term u into t? We get L. Okay, now next quantity what we have is basically half a t square over here, right? So very simple, half obviously it's a numerical quantity, so we don't have the dimension, right? Yes Akshay, you actually got that right. So acceleration is given as L t to the power minus 2, the dimension, and acceleration of time over here is t, right? Dimension of time over here is t. Now we have t to the power 2. So again t to the power minus 2 plus 2 cancels, we get the dimension L. So on the right hand side we have the dimension L over here, on the left hand side also. So on the left hand side we have L, on the right hand side also we got the dimension for both terms together. I mean this term is also L, this term is also L. So because the dimension on both sides are both sides of the equation has the same dimension, we can say this equation is dimensionally correct. Okay, so let's try one more equation. So in this case if you see, let's take one more equation, that is, let's say we have an equation half mv square is equal to mgh. Kinetic energy in this case is equal to potential energy. This is what we have, okay? So let's check whether this equation is dimensionally correct. Very simple, write the dimension formula on both sides, okay? So on the left hand side if you see, on this particular side, the dimension of mass is m, the dimension of velocity if you take, velocity is nothing but L t to the power, okay, L t to the power minus 1 L square, so the whole term square, okay? So on the right hand side if you see, we have mass, okay, and g is nothing but acceleration due to gravity, so we have L t to the power minus 2, okay. H is what? Again h we are talking about displacement, right? So again h is displacement in this case. If you see, this is dimension, it has the dimension of length, so L over here. So here we have m, L to the power 2, okay, t to the power minus 2. On the same side, on this side what do we have over here? This side again we have m, this is L into L, this is L to the power 1, L to the power 1, again this will be L to the power 2 over here, t to the power minus 2. Okay, so from here what do we get? We get the dimension on both sides, okay. What we can see, the dimension on both sides are same, which means this equation is actually dimensionally correct, okay. So this is the second application. Now the third application is to derive relationship between different physical quantities, for which again we make use of homogeneity of dimensions, okay. We can derive an expression for a physical quantity if we know what are the various factors on which this particular physical quantity depends upon, okay. Very simple. Let us derive the expression for centripetal force, okay. When do we have centripetal force? How do we get centripetal force? Very simple. Let us derive the expression for centripetal force acting on a particle, okay. The particle has a mass m, and in this case what we are saying, this particular particle over here has a mass m, and at this point what we are saying, it has a velocity v over here, okay. And if you see, from the center of the circle, the radius it has is basically r, okay. From the center of the circle, the radius of this particular quantity if you see is basically r. So we know there is an object is going in a circular motion, and in this case, for example, take a stone, tie it to a thread and actually rotate it. What we see, the object has a centripetal force. There is a centripetal force exerted on that object to keep in its circular motion, right? So let's derive an equation using fundamental quantities in this case, right? So here what we will know, we want to derive an expression for force, right? So what are the different quantities involved in this case? So for example, in this case we have mass. We don't know to what mass to what power it is, right? So we'll write it as m to the power of a. The next fundamental quantity that we have is velocity. We don't know to what power it is. Is it v square or v to the power minus 2 or v to the power 5? We don't know that. So right, v to the power b over here, right? We'll give it a variable, and the next quantity that is involved is radius r, okay. So we'll say radius r to the power c. Now In this case, what we are saying, to remove this equality sign, let's introduce a constant k. Okay, so this is the equation we have. Now both sides write them in terms of their dimensional formula, and k over here is a dimensionless constant. Okay, k over here is a dimensionless constant. Now what is the dimensional formula of alright, so let's check that, Akshay. So here force over here, if you see, force is actually equal to, what is the dimension of force? Force is actually m, dimension of force is m, L to L, T to the power minus 2, right? So k is a dimensionless constant, so you can take it as 1, right? So 1 into, what is the dimension of mass? M. Okay, so here we have m to the power of a. Similarly, what is the dimension of velocity over here? Velocity is nothing but L T to the power minus 2 to the whole power b. Okay, then finally we have the dimension of r over here. Dimension of r is basically L. Now L again, because it has the dimension of length, so L to the power c, right? So on this side we have m to the power 1, L to the power 1, T to the power minus 2. Okay, so then this side, let's write over here, we have m to the power of a, this is one term. Okay, on the next term over here, okay, okay, then you can actually take in the quantity r also, Akshay, and then calculate. And over here we have L to the power of b, T to the power, bring the power term inside, minus 2b, L to the power c, right? So obviously over here what we have, these two quantities are similar, so obviously instead of writing L to the power b and c, we can write it as L to the power of b plus c. Now what we see in this case, we are seeing on both sides the base terms are same, right? So we can equate the power terms. So over here, if you consider the values for a over here, obviously on this side we have a is equal to m is equal to the powers of m, if you see, that is nothing but a is equal to 1. So we got one value, a is equal to 1. Consider the powers of t. Next let's take the powers of t over here, right? Powers of t, if you see, what do we get over here? L, actually over here it will be alright, so we end up getting, okay, so next term we end up getting is t to the power, I am really sorry over here, I'm really sorry guys, just a second, this is my bad. So what I had done is t to the power 1, right? Yeah, mass into acceleration, t to the power minus 2, this is actually right. So I'm really sorry. So this velocity term is actually 1. Okay, this term is actually 1. So here we get t minus b. Okay, very simple. Velocity is given as L T to the power minus 1. Okay, so t to the power b. So t to the power b. So the second term, if you consider, okay, let's consider the powers of t. What do we have as the powers of t? We have minus 2 is equal to minus b. Obviously we know b is equal to 2. So we got two equations over here. Next let's see, next what we have over here, the powers of L, the powers of the term L. So b plus c is over here is equal to, on the powers of the L, on the left hand side we have 1. Okay, b we already know, in this case, b is going to be, b is basically 2, right? So 2 plus c is equal to 1. So c will be equal to what? 1 minus 2. So c is going to be minus 1. So we got three quantities, which is a is equal to 1, b is equal to 2, c is equal to minus 3. Substitute the same in this equation that we have over here. Okay, so here f is equal to, right, f is equal to k, this constant is basically, let's take that k, it's a dimensional constant, okay, and m to the power what? M to the power a. M to the power a is what? 1. Okay, then we have v to the power b. V to the power b is 2. R to the power c. R to the power c. C is minus 1. So f is basically equal to k m v square. R, you bring it down, it will come down over here, right? So from here we get, okay, f is equal to m v square by r. From experiments you can find that k is actually equal to 1. Okay, so from here you end up getting f is equal to m v square by r, which is basically the dimensional formula for which is actually the formula for centripetal force. So we have derived the expression for centripetal force. Okay, so these are the three applications of dimensional quantity. So once again, the last question for today: what are the applications of dimensional quantity? So you can give it the answers in the chat box again. To convert a physical quantity from one system of unit to another, to check the correctness of a given physical quantity, okay, and to derive a relationship between different physical quantities, and all of the above. Which of the following do you think is the right answer? Right? All of the above, that is actually right. All of these are applications of dimensional quantity. Alright. So once again guys, tomorrow we have a class at 7:45. We will be discussing about dimensions and applications of dimension, and this class happens on the Unacademy platform. So you can join in. It's a completely free session, so all of you can join in. If you have any doubts, you can ask. We will do more numericals, and if we can discuss, if you have any doubts in any other topics, especially if you're having any doubts from dimensional analysis, again you can ask me in that class as well. Alright, then I'll see you all tomorrow. Take care, and if you like the class, please share it among with your friends. Like the class and share it among with your friends, and do subscribe to the channel so you can get notified whenever the class goes live. Alright, so I'll see you all in the next class. Bye.